Hello everyone. In this lesson, we are going to have a special subject, the MIMO systems and the space-time coding. The MIMO is a shortened form of multi-input and multi-output. There are three problems we are introduced today. First, we are introduced the capacity of MIMO channel, and then we are talk about the space multiplexing, which is one scheme of MIMO system. And finally, we are introduce the space-time coding, which is another scheme of MIMO system. Okay, let's start from the first problem, capacity of MIMO channel. With the development of society, there's much requirement for information exchange. So, high-rate communication service is required. Then, on one hand, we need more channel capacity. And on the other hand, we also need more advanced communication technology to exploit such capacity. We can see from Shannon's formula, this expression, please think what methods can improve the channel capacity. It's easy to know. One method to increase channel capacity is increasing bandwidth. Okay? And another method is increasing transmit power. However, there's shortage for increasing bandwidth. First, we know the frequency spectrum resource is limited and precious. So, it is not easy to increase the bandwidth for communication system. And also, for more bandwidth, we'll generate multi-path influence. You know the multi-path influence. So a channel with multi-path influence will make the channel become frequency selective fading. For such fading, it is harder to make channel estimation and to do equalization. And there's also shortage for increasing transmit power. Let's see an example. Please see, this is a system for single antenna system, for single antenna with QPSK modulation. For this modulation, each symbol can transmit 2 bits information. We can see this picture is the BER over SNR curve. This green curve is a BER for QPSK modulation in single antenna system. And if we want to increase information rate doubly, what can I do? It's easy to think that we can use 16-COM modulation, okay? For 16-COM modulation, each symbol can transmit 4 bits information. So the rate is double. However, for 60-COM modulation, about 6 dB more transmitter power is required. Okay? If we want increase information rate double again, it's also easy to consider. We can use 256-COM modulation. Okay? If we want to increase information rate doubly again, how can we do? It's also easy to consider. Using 256-COM modulation. For this modulation, each symbol can transmit 8 bits information. However, about 12 dB more transmit power is required. So, basically, we can say to improve information rate by increasing modulation orders, much more power is required to transmit. And actually, that is not practical. Why? Considering the device level and environment and the health to human, that is not practical. So, actually, we can use another effective method to improve channel capacity. That is, to parallel connect multiple channels. So the capacity of parallel channel is the sum of the capacity of each of all the sub-channels. So constructing multi-input and multi-output channel by using multiple parallel channels can improve the capacity. This is the foundation of MIMO communication. Let's see, this is a MIMO system. We use multiple antennas in the transmitter and multiple antennas at the receiver as well. So, we know MIMO system is proposed by these two persons, Tanaka and Fortini, who both from the Bell Lab. So in the time about 1998. And MIMO is to use multiple antennas in both sides of transmitter and receiver. And at the same time, all the antennas use the same frequency spectrum, so there's no extra frequency spectrum needed. And please note that the MIMO system requires that the channels of all pairs of transmitter-receiver antennas are independent on each other. So this is a condition. see this expression, which is the system model of MIMO. Y is a receive vector, and X is a transmit vector, and H is a channel matrix, and N is a noise vector. Actually, a MIMO system can be transformed into multiple parallel channels. So, and these multiple parallel channels are mutually independent. So, the capacity of the MIMO system is k times of the capacity for single antenna system. Okay? What is K? The K is a minimum of NT and NR. The NT is a number of transmitter antennas, and NR is a number of receive antennas. Okay? What is the advantages of MIMO system? First, let's see this picture. The x-axis is SNR, and the y-axis is the capacity. We see the blue curve is the capacity for single antenna system, so it's also the capacity from Shannon formula. And the red curve is the capacity for 6x6 MIMO system. So we can see from this picture the capacity of MIMO system increase faster than that of single antenna system. Okay? So, one important advantage of MIMO is improving capacity. And the MIMO system have also another advantage, which is to improve the reliability. We can see from this picture the x-axis is SNR, and the y-axis denotes the bit error rate. See, the blue curve is a bit error rate for the system with single antenna, and the red one is a BR for 2x2 MIMO system. We can see with the increasing of SNR, the BR of MIMO system reduce faster than that of single antenna system. Okay? According to the two advantages of MIMO system, there are two schemes to utilize such a MIMO channel. First, in order to improve the efficiency, people proposed the space multiplexing, which is a method, which is a scheme for MIMO system. And besides, in order to improve the reliability, people propose the space-time coding for MIMO system, which is another scheme. First, let's introduce the first scheme, space multiplexing. We can see from the example, which is a space multiplexing system with two transmitter antennas and 2 receive antennas. See this picture from the source. The bits from the source will be splitted with 2 ways. For any ways, the bits will first be processed by DSP model and then sent to radio. And finally, we can use the antenna to transmit. Okay? And for the receive side, there are also 2 antennas. For any antennas, the signal will be sent to radio model and sent to DSP model. And finally, the signal, the bits in the 2-way will be combined into 1-way. And finally, the bits, all the bits will be recovered at a receiver. Okay? This system can also be abstract as this model, this system model. So, see this model, system model, we can know first, the transmitted data is sent by 2 antennas instead of one antenna. So, more efficiency is obtained than that of single antenna system. And also, all the antennas will use the same frequency band. So, no more bandwidth is required. Okay? And also, each transmit antenna just use a half of power. So, no more transmit power is required compared with that of single antenna system. There is a condition to do that for MIMO system. The condition, all the channels will be independent on each other. And also there are disadvantages for MIMO system. We can see each receive antenna will receive the transmit signal from both transmit antennas. Okay, so the decoding complexity is more than that of single antenna system. We can see the performance of space multiplexing. This is BER and BER over SNR curve for the comparison between seesaw system and 2x2 space multiplexing. You know, the seesaw system is corresponding to MIMO system. For MIMO system, for both side of transmitter and the receiver have multiple antennas. And for seesaw system, both sides of transmitter and receiver has just one antenna. This simulation is done over QPSK modulation and under the relay fading channel. Okay, we can see the blue curve is BR4 for seesaw system, and the red one is for 2x2 space multiplexing. it's easy to see from the picture that. So first, for the same SNR, the MIMO system have lower BR, okay? And we can see from another way, for the same BR, the MIMO system have about 4 dB gain over SNR when the BR is 10 to the power -2. So, which means if we want to get the same performance, MIMO system will use much less transmit power, okay? And we can consider another problem about the efficiency. We say MIMO system have double information rate compared with the CISO system from this picture. Why? Why? Please think that. So we know for 2x2 space multiplexing, which have 2 antennas for transmitting information, okay? And each antennas use QPSK modulation. So each antennas can transmit 2 bits per signal. But this MIMO have 2 antennas, so 4 bits information can be transmitted for each single time, okay? And the CISO system just 1 antenna, and use QPSK modulation, just 2 bits is transmitted for each single time. So such a MIMO system have the double information rate than that of CISO system. We can see MIMO system not only improve the performance, but also get the double information rate. These is the advantages of MIMO system. However, the space multiplexing scheme have also the limitations. First limitation, the space multiplexing require number of receiver antenna no less than the number of transmitter antenna. So the NR is equal to or more than NT. And actually, this condition cannot be satisfied in some case. Which case? For the case of downlink. In the downlink, if we required receiver use many antennas, it cannot be completed sometimes, because for mobile terminals there's limited volume and limited power, okay? So the mobile terminals cannot be equipped with multiple antennas sometimes. This is one limitation. And another limitation, we know the space multiplexing is to improve transmission rate, but the ability to resist the feeding channel is not obvious. So, in some case, where the SNR is very low, the space multiplexing cannot perform well. To resolve such two limitations, we know there's another scheme for MIMO system, which is space-time coding. Okay, let's see. This is a system model of space-time coding. Space-time coding was proposed by these two persons, Torok and Alamotti, in 1998. So from this model, we can see S1, S2, Tier 2, SNS is the output from the modulation. So they are symbols. Okay? We make space-time coding for these symbols. We can see the x-axis is a time. So there's we suppose there's t symbol time slots, and the y-axis denote the antennas, denote the space. So which denote the NT antennas. Okay. So we can get a T by NT space-time positions. We use the T by NT space-time positions to make space-time coding for these symbols. And each position, the symbol in each position is a linear combination of the transmitter signals, transmitter symbols, and the conjugate of them. So the code words of space-time coding is a space-time matrix, which can expressed as this matrix. Okay. Also, there's two advantages. First, we can design suitable redundancy symbols among space-time positions. Okay, design redundancy among these positions to obtain space diversity gain. The benefit for diversity gain is to resist channel fading. Okay, this is the first advantage for space-time coding. And another advantage, there is no requirement for the number of receive antenna. So the number of receive antenna can less than the number of transmitter antenna, and even which can be one. So which is very suitable for downlink communications. You know, because for downlink communication, the receiver usually is the mobile terminal The mobile terminal can just be equipped with just one antenna sometimes, because the limited volume and limited power. Okay? So we can see the space-time coding scheme resolve the problems which cannot be resolved for space multiplexing scheme. Okay? Okay, let's see the property of traditional channel coding. We first analyze the property of channel coding, and then give a comparison for the space-time coding. This is a 7 and 6 leading code. Okay, this is equations for check equations to generate the check bits. This information sequence, and this side is the code words. We can see for each code word, the first 3 bits are the information bits, and the last 4 bits is the check bits, which are generated by these equations. And we know the check bits are also the redundancy. And we also know there's correlation between the information bits and the redundancy. Okay? So, briefly to say, the traditional channel coding is to make a code at a bit level. Okay? The first property. And the second property, it is to design correlated bits along time domain. To design correlated bits along time domain. So, to do that, can correct error. So, the channel coding is also named error correction coding. And another property, due to redundancy along time, the information efficiency must be reduced compared with uncoded system. So that is obvious. Okay? And next, let's see the property of space-time coding. These are 2 space-time codes. And first, let's see the first one. First one is 2 by 2 space-time code. We see the 2 position. The symbols are in the 2 position are correlated. Okay, and another two positions are also correlated. Okay, and we see another space-time code, which is 4 by 4 space-time code. We can see the symbol in the 2 position are all from the same symbol x3. Okay, so they are correlated. Similar case exist in other positions as well. So we can say, first, the space-time coding is to make coding at a symbol level, not bits, because we see the symbol at each space-time position as the output from modulation. Okay, from modulation. So they are symbols instead of bits. This is the first property. And another property, it is to design redundancy symbols over space and time domains. The aim to do that is to resist channel fading. So which is different result of channel coding. The third property, we know space-time coding is done at a symbol level after modulation, and traditional channel coding is made at a bit level before modulation. So these two kinds of coding method can be used at the same time. So space-time coding can be used combining with channel coding. You know, this is the third property. And the last one, how about information efficiency? So we have mentioned before, the information efficiency will be reduced for channel coding, okay? And how about for space-time coding? Let us see some examples. These two space-time codes, the first one and second one, okay? We can see from the first code word, there are two symbol time slots. There are two symbols transmitted. So the rate is one symbol per symbol time slot. It's easy to understand, okay? For the third one, there are also two symbols. There are also two symbols transmitted. And also, there are two symbol time slots. So the rate is also one symbol per symbol time slot, which is the rate of seesaw system. The rate is the same with the seesaw system. So the information efficiency is not reduced compared with that of seesaw system. Okay? See another code word. This is a space-time code with 4 by 4. We can see there are just three symbols transmitted, but it uses 4 symbol time slots. So see the x-axis is the symbol time slot. Okay, there are 4 symbol time slots. So the rate is 3/4, it is 3/4 symbol per symbol time slot. So such a code have a rate which is less than seesaw system. Okay, let's see another example. This is a code for golden. This is a code, lambda is golden code. See, there are also 2 symbol time slots. But in the 2 symbol time slots, there are 4, x1, x2, x3, x4. There are 4 symbols transmitted. So the rate is 2 symbols per symbol time slots, which is a rate more than that of scissor system. So briefly to say, the fourth property of space-time coding. Space-time coding does not necessarily lose information rate. Compared with uncoded single antenna systems, and even it can increase the information rate for some codes. So this is for the last example. The information rate is increased compared with that of scissor system. Okay. In summary, space-time coding is a technology using minimum error ratio criterion to design suitable symbol correlation over space and time domains, and 4, obtain the velocity gain and the coding gain. 2, resist channel fading. And what is the velocity gain and the coding gain? Let us see the parameters of space-time coding. The first 2 parameters are the velocity gain and the coding gain. In order to introduce the 2 gains, first, let us see the system model of space-time coding, which is this expression. Y is a receive matrix, and this coefficient is a normalization coefficient for power. And C is a space-time code. H is a channel matrix, which unchanged within one code word and changing independently between different code words. Okay? And N is a complex Gaussian white noise matrix. According to this system model, people give the pairwise error probability for this expression. This is a pairwise error probability. See, this expression, the R is a rank of the difference of any 2 unequal code words. And lambda I is R non-zero eigenvalues of this expression. Okay, and then we can give the definition for the velocity gain and the coding gain. The velocity gain is also named the velocity order. So, if the minimum of rank C minus C minus another code word, okay? So the R mean is the rank. Then the velocity gain of code is R mean times NR, which NR is the number of receive antenna. When R mean is equal to NT, the NT is the number of transmitter antenna, then the fault velocity is obtained, which is NT times NR. So this is the definition of a diversity gain. And for the coding gain, which also named diversity product, if R mean is equal to NT, we can define the coding gain as this expression. So this expression is a little complicated, so we will not explain more. We can explain the coding gain and the diversity gain from this picture. This curve is an error ratio curve over SNR. We can see diversity gain can be denoted by the scope of the curve. A code with more diversity gain, the error ratio curve of that will reduce faster. Okay? And the horizontal distance is denote the coding gain. A code with more coding gain, the curve will be lower. Okay? So we can see a code with more diversity gain and the coding gain, the code have better performance. Okay, another parameter about space-time codes, the code rate, which is a parameter to express the efficiency. Let us see is a T by NT space-time code, and where T is a number of symbol time slots. If C includes NS complex symbols in it, then its code rate is defined by this expression. So the code rate is equal to NS divided by T, which denotes the number of complex symbols transmitted by each symbol time slot. Okay? And there are some special cases for code rate. First, the space-time code with rate 1. What does it mean, the rate 1? The rate 1 is the same efficiency as that of single antenna uncoded system. So, obviously, each symbol time transmit just one symbol, so the efficiency is the same as the single antenna uncoded system. Such as multi-code, the sum of QSTBC, which is quasi-orthogonal STBC, and diagonal algebraic STBC. These codes have the rate 1. The rate 1 space-time codes show us that using multi-antenna can obtain fault diversity gain and some coding gain, but does not lose efficiency compared with scissor system. Okay? And another special code rate is the four-rate space-time codes. What does the four-rate means? First, the four-rate is the minimum of NT and NR, which denotes the number of transmitter antenna and the receive antenna respectively. And such as golden code and perfect code. These two kinds of space-time codes have four-rate. The four-rate space-time codes show us these codes not only have full diversity and some coding gain, but also achieve the same rate as space multiplexing system. So, such codes have the most code rate. Okay, let's see the next parameter, which is coding complexity. We know in order to obtain the full diversity, usually the space-time codes have to use ML decoding. So you should know ML decoding. So the coding complexity is determined by the number of symbols which need to employ joint ML decoding. So we can see from this picture the y-axis is decoding complexity. The x-axis is modulation orders. We can see the decoding complexity is an exponent function of the number for joint decoding. So, our space-time codes have less number for joint decoding. Such a code will have smaller, much smaller decoding complexity because they are exponent function relations. Okay, let's see another parameters. Power balance. So a code with power balance is to say the power of a space-time code is equally distributed over all space-time positions. Let us see the first code, which is Alamotti code. All the power is distributed equally over the four positions. Okay? But for the second code, which is DAST code, the power just is distributed at the first position and the fourth position. And another two positions are 0. So, which is not power balance. Obviously, a code with good power balance, this code will have lower PAPR. you know PAPR is peak average power ratio. Okay? And another concept, decoding delay. What is decoding delay? For code with a dimension of t by nt, we know the t is a number of symbol time slots, and the t is also named as the decoding delay. Why? Please think. For space-time code, we have to wait the time t to receive the whole code, and then we can do decoding. Okay? So the t is also named as a decoding delay. And please note that space-time codes often requires a condition. The number of symbol time slots should no less than the number of transmit antennas. So, a square matrix code, which is nt equal to nt, has an optimal decoding delay. Because for usually nt should equal to or more than t should equal to or more than nt, and in the case t is equal to nt, such code have the optimal decoding delay. It is not hard to understand. Okay, finally, let's give a conclusion for the goals to design space-time codes. To design a space-time codes, we should, to achieve the full diversity and to obtain the high code rate. And also, we hope to get the large code gain. And then, we also hope such a code have low decoding complexity and with the property of power balance, and also has small decoding delay. And actually, there's no any codes can get all the advantages of these properties. Actually, we have to do trade-off. So, any code just have the trade-off for all the properties and cannot get all the good properties. So that is what we want to talk today. Thank you.